Welcome back to Mathematical Statistics. It is almost the weekend and it is very fall-like, and I might actually get outside, which I haven't been all semester. So I hope you guys can.
Well, not terrible anymore.
What?
Are the fires still smoking? I don't know. I haven't been hiking the past couple weeks because the air quality is terrible.
Yeah, I don't know. I haven't heard an update from yesterday. Estes Park was evacuating, and that was really horrible. And I don't know what's going on up there. I just mean I want to get outside. Like, I don't have to go anywhere. Just like step outside. So I think I can manage that. Today's colloquium is a really interesting and important speaker, and he's really fun to listen to. So I'd encourage you to come if you can do it. And if you can't, but you are available, can you just log in on Zoom and then turn the camera off and do something else? I need to make sure he has a big audience because he only committed very recently and I didn't get to advertise it very well. But a very cool guy. So welcome back. Oh, yeah.
What time is that today?
It is at 4:10.
Okay.
And does everyone have the link? Just find the link. There's a funny story behind this guy. I mean, behind why he's here. While I'm finding the link. I was in charge of the colloquium once many years ago, and we were having a special department celebration. It was some kind of anniversary thing. And I was getting ready to introduce him when someone who I will not name told me that I was not important enough to introduce him. And so I invited him. I was like, I just want to introduce you. Will you come here? So that's what happened. Okay, so I just found the link, and that is at 4:10. And no, you're not going to let me down if you're not there. I'm just throwing it out there. Okay, so we were talking about the, homework. We weren't talking about that, but how's that going? Number 1, very short. Also, number 3, very short. While it might look scary, number 3 is just the weak law of large numbers. So just to, I don't know, if I get you started, it's done, but I do want to say at least something about problem 3 on the homework. So we have the a joint PDF, is of IID things is equal to, yeah. And why do I keep making that noise? Thank you. You're not seeing like the reflection in my eyeballs or something? Okay, we have a joint PDF, and because we have IID things in this problem, it comes from a product of individual PDFs. And the likelihood is any function proportional to the joint PDF when you fix the x's and you start to think about it as a function of theta. And we've written down a bunch of likelihoods and we've dropped some constants, but for this problem, it's actually meant for you to keep everything. And so we have a likelihood function that is the joint PDF. In general, it could be just proportional to the joint PDF, which is this product. Okay, And then in this problem, you're looking at the log likelihood function. And then I did include a subscript n here just to emphasize the dependence on n, because we're talking about convergence. And if there's no sample size moving, it can look a little weird. But this is the log of the likelihood. And this is the sum as I goes from 1 to n of f of xi and theta. And so you were asked to think about this likelihood with random variables plugged in. So you have this L of theta, or L sub n of theta, which is the sum as I goes from 1 to n of f of capital Xi and theta. Just trying to be ridiculously clear on that capital letter. And finally, note that what you're looking at in the problem is a sample mean. Think weak law of large numbers. What does any x bar converge in don't say it, but converges in probability to? I mean, this is assuming you didn't bother to write all this out. The actual solving of the problem is kind of a one-liner. And yes, problem 1 is very short as well. So no, you didn't do it wrong. Okay, do you guys have any of your own questions, or are we going to talk about this Monday? Okay, so last time we introduced the Cramér-Rao lower bound, and it is a lower bound for the variance of all possible unbiased estimators of a thing, the thing we're calling tau of theta. And so we want to estimate some tau of theta for some distribution, and it may be that tau of theta is theta. And so for any unbiased estimator, which we were calling a statistic T. So the unbiased estimator you might call tau theta hat, but really it's a statistic. So in more of a statistic notation, we'll just use a capital letter. So that is a statistic, which is anything you can compute from the data. We showed that under certain regularity conditions that the variance of T is greater than or equal to tau prime of theta squared over this thing that we call the Fisher information. And there's an I sub n there because it depends on all n pieces of data, x1 through xn. And we define it as the expected value of the square of the derivative with respect to theta of the log of the joint PDF with the capital X's plugged in. Otherwise, the expectation is really boring. And that whole thing gets squared. And we computed one last time. And you don't have to worry about the regularity conditions, just only that you can't do this whenever the parameter is in the indicator. That was part of our proof. Something would fall apart. Okay, so we were just starting in on 3 computational simplifications for the Cramér-Rao lower bound. And so we had already proved what I called computational simplification number 0. I'm kind of changing my mind about this and wanting to call it 1. But in my notes, I think I called it 0. And the point of that was that this is not something you're going to use for computing Cramér-Rao lower bounds or Fisher information. It's something I need to prove other properties that I think you would use. So computational simplifications. I've got 2 for you, and they can be used together. So simplifications. Okay, so last time I wrote down property 0, and that is that the expected value of this derivative that defines the Fisher information without the squared, this expectation is always 0. So it looks just like what I wrote down before, but there is no squared. And just for your information, I'm not really going to be calling it this, but the thing inside the expectation is known as a score function in statistics. So if you hear those words in another class, you could say, I've at least heard that before. Okay, so I know I already proved it, but it was really short and rushed, so let me prove it again. The expected value here, now this is a function of all of the x's. So I need to write this function with a lowercase all of the x's and put it in front of the joint PDF for all of the x's and integrate. So this is the integral of d theta, the log of f of the little x's and theta, and then that gets multiplied by f of the little x's and theta dx. And if you're taking the derivative of the log of something, you get the derivative of the thing over the thing itself. And by the way, that integral is over the entire space, and it is representing actually n integrals. And the dx with a vector is representing dx1, dx2 through dxn. But I'm going to take the derivative of that log, and this is the derivative with respect to theta of the joint PDF. I said I was redoing this because I was rushing last time, and yet I'm kind of screaming through it this time too. Times the joint PDF. And so we get some cancellation, and we get the integral d theta of the joint PDF. And if we pull the integral out, which is one of the assumptions that we make for proving the Cruméra lower bound, so you can't always interchange derivatives and integrals, and you especially can't interchange them when the integrals involve the theta, like you can't move the d theta past that. But there's also some other cases where you get something that converges to something one way and not the other. You're not going to have to worry about it in this class, but we did assume that we can do this. So we can pull this out. And now we are integrating the joint PDF over the whole space. Again, that's an n-dimensional integral. So we get d theta of 1, and we get 0. I always write those 2 slashes at the end of my proofs, and always in my head, I am thinking happiness ensues. Just stupid, but I can't stop thinking that. Happiness ensues when I've successfully proven something. Questions? Okay, so what, really? Because I think I'm giving a rushed vibe today, and you probably don't want to ask questions because you think I'll freak out. Okay, so, or you don't have any. Okay, so computational simplification number 1, really the second thing in this list, is going to be a way to remove the squared in the expectation and replace it with a second derivative calculation. So this looks like this. It says that the expected value of, basically I'm going to write down the entire Fisher information term here. This is the derivative of the log of f of the vector x and theta, and the whole thing gets squared. I claim this is the same thing as the negative of the expected value of the second derivative without the square. Now, sometimes this is a computational simplification and sometimes it makes things worse. But last time we did an example where we computed this thing inside and we squared it, and we noticed that the whole thing with the square looked like a variance, and we could tell what with the expectation looked like a variance, and we knew what it was. But sometimes when you take another derivative, or when you're taking derivatives in general, the function could be getting simpler. Like if you had a theta squared, now it's a theta, now it's a 0. If it's getting simpler, you might want to consider this, this technique for finding Fisher information. Of course, sometimes taking derivatives makes things worse. So you don't necessarily want to use this, but let's prove it. Okay, so I'm going to start with what we wrote down in computational simplification number 0, and that's where we said that the expected value of the derivative of the log of f of the vector x and theta, this is 0. So I'm going to write out what the left side is. This is an integral of the thing times the joint PDF. And that's equal to 0. Okay, so I want to see a second derivative in here. So I'm going to take the derivative with respect to theta on both sides here. So I'm going to do a d theta on this whole thing equals d theta of 0. And that right-hand side is, of course, 0. And on the left side, I'm going to pull the derivative inside the integral, which we're assuming we can do. And then I'm going to take the derivative of the integrand using the product rule. And then that will give me a sum of things that I can run the integral across. So doing all of that at once, my first integral, so I've got like a first thing and a second thing. So I'm going to take the first thing times the derivative of the second thing. And then the second thing times the derivative of the first thing. And that's, of course, a sum. So I'm running the integral across. So this is now going to be a second derivative of the log of f of x and theta, and then just an f of x and theta dx. And this whole thing, why don't I just write smaller? This whole thing is equal to 0. It would be nice if I got these things on one line. So all I did was take the derivative of this product. And let me know if there's anything I can clear up. Oh, did I have a, what did I do? Okay, yeah, I'm fine. Okay, so the second term there appears to be really what we want. This is a function multiplied by the PDF and integrated over the whole space. So this is in fact the expected value of this if you put the capital X's in. But let me not write that down yet. Let me simplify the first term. I've got, well, let's see where we want to go. So look at what I'm trying to prove. I want that second derivative, at least it's negative, to equal like a square of the first derivative. And I can do that back here. So I've got a first derivative and then a derivative of the joint PDF. This integral, as stated, doesn't look like an expectation because we need to multiply by the joint PDF. I'm trying to force it to look like an expectation. So I'm going to write the first integral as the derivative with respect to theta of the log of f of x and theta. And then that second term, I want to turn it into a derivative of a log. So if I write the derivative with respect to theta of the log of f of x and theta, that thing is the derivative of f, which is what we have there, over f itself. So I need to multiply by f to cancel that extra denominator that I've created. Move you over. So again, what I did here was I rewrote this as the derivative with respect to theta of the log of the f, and then I multiplied by f. And two things motivated me to do that. One is I wanted to see like a d theta squared, and I also wanted it to be an integral with just the PDF at the end, so it looks like an expectation. Any questions?
So when I see something like this, like doing the product rule and then subtracting something to another side, it kind of just looks like integration by parts. Is there some
Yeah,
pedagogical reason why this is more straightforward to use as the product rule?
not really.
Okay,
Yeah,
it's just fun. I like the product rule better.
yeah, by all means, do integration by parts if you want. I guess, no, there's no real reason.
Well, integration by parts is like the inverse product rule, right?
Yeah.
In a sense. So I think there is maybe some connection there.
Oh, there's definitely a connection. It would be equivalent. You can do this, you can prove this with integration by parts. But I guess what I was trying to say is, why did I choose this way? I don't know. Okay, so then there's the second term and then equals 0, but I'm running out of space. So this first term, I've got this thing squared times the PDF. So that's the expected value of that thing squared with the capital X's plugged in. So that giant thing I just circled is the expected value of the derivative with respect to theta of the log of f. And now that I'm translating it to an expectation, this is the capital vector x. And this whole thing squared. That's what that circled thing is. And then the second part is this guy, is this pink circle. And that is a second derivative integrated against a PDF. So that is the, I wanted to keep it pink for color coordination, but I think that's kind of hard to read. So let me go back. That guy is the expected value of the second derivative of the log of f of capital X and theta. And that whole thing is 0. And so we're done showing what we wanted to show, because this left-hand side is the Fisher information. And if you move that expectation with the second derivative in it to the right-hand side, that's exactly what we wanted to show. So it's equal to the negative of the expected value of the second derivative. So after I show the last property, we're going to see examples of using these computational simplifications, but is there anything I can clear up? I have to say, it took me a long time in my mathematical career to embrace this one, and I don't know why, because it makes things so much easier most of the time. I used to teach it like, here it is, if you want to use it, I guess, but we're going to use it. Okay, so my second property, or third really, is specific to IID random variables, which is what almost everything is for this class. So for this one is super important. And now I kind of think the other one is super important. But for x1, x2 through xn, IID from a distribution with a PDF f of x and theta. In other words, you get the joint PDF by multiplying these guys together. We can say that the n-dimensional Fisher information is equal to n times the one-dimensional Fisher information. So the n represents the length of the vector, right? And this n-dimensional Fisher information was first defined to be this derivative of the log of the vector x, blah, 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 blah. And so the one-dimensional Fisher information is going to be if you only use a vector of length 1, which means only one random variable and nothing joint going on. Now you can combine this property with our previous property and also relate, you can write both of these as a negative second derivative. So we can combine these properties. All right, let's show it. This is actually, I was going to say this is actually worth showing, but I think so many things are worth showing. But there's parts of this proof I think you're going to find useful later, and it's not very hard. So let's prove it. I'm going to start with the left side. The expected value of the derivative with respect to theta of the log of f of capital X and theta all squared. I'm going to write out that joint PDF is a product. So I don't want to give this its own whole line. So let me just sneak this in here. This is a product as I goes from 1 to n of an individual PDF with an individual xi plugged in the IID case, since IID. So the log of that is going to turn into a sum of logs. And let me do multiple things in this one step. maybe not. Okay, so let me write this down. The derivative with respect to theta of the log of a product and that whole thing gets squared. And that is, of course, a sum of logs. I meant to do that. I mean, I meant to already. That's the whole reason I wrote that product up there. I wanted the next line to be the derivative with respect to theta of the sum of the logs. That was a total fail in me trying to get away with not writing a line. I actually wrote it twice. Right, and the derivative can come inside the sum. Definitely no problem there because it's a nice finite sum, so you don't have any convergence issues. And yeah, so I've got the expected value of a sum as I goes from 1 to n of the derivative of the log of the f of xi and theta. And that whole thing gets squared. And so one way I can figure out this squared thing is by treating it as just two copies of the sum multiplied together. So I'm going to take the sum as I goes from 1 to n, the derivative with respect to theta, the log of f of xi and theta, and then I'm going to multiply that whole thing by the same thing with a j. No. Come back. What? I hate cut and paste, but I'm really trying to make it work. And that's not even going to fit. Sorry. Sorry. I am going to write this as the expected value of the sum as I goes from 1 to n of the derivative with respect to theta of the log of f of xi and theta, and multiply that by the sum as j goes from 1 to n of, the same thing, but with a j in place of the I. And so that's going to be the same thing as a double sum. Is that okay with everyone, that a product of sums is a double sum? You could think of this as a constant that is pulled inside of this sum, and then you get to write it as a double sum. Expectation is a linear operator, so I get to pull these guys out. And now we have to figure out some of these terms. So there are two kinds of terms I need to be concerned with. One type is when j equals I, or I equals j terms. You know what? Let me not do that one first. Sorry. If j is not equal to I, then we're talking about something like the expected value of the derivative with respect to theta of the log of f of xi and theta times the one with the j. So these are really bizarre random variables. The random variables put through functions, but these guys are independent if I is not equal to j, and that's because xi is independent of xj. So just because we put them through a log and a PDF and took a derivative did not somehow induce independence. And so that means you get to say that this is the expected value of the first guy times the expected value of the second guy. So both of these we already know, even though we didn't do it one-dimensionally, these are both 0. These are both cases of property 0 with n equals 1. Like if you could just go through the proof of 0 with just one x and not the vector, or you can go through with the vector and say the vector length is 1. But these are both score statistics inside expectations. So this is 0 by property 0. Does that make sense? So the only terms we care about, especially if you think of organizing all of these in an n by n matrix, the only ones we care about are on the diagonal. And there's n terms there, and they're actually all IID because if I equals j, then we're talking about the expected value of a thing times a thing, and they're the same. So we get the expected value of one of them squared. And that is our Fisher information term, except we don't have the vector of x's in there. So this is the one-dimensional Fisher information. It's exactly how we defined it, except we have a, don't write that vector, but we have a vector of length 1. And out of the sum back here, if you again think of arranging them in a matrix, we only have n things on the diagonal to consider. So man, I didn't do this very nicely. Let me go up here and just put like a star back to the thing I was summing before I started looking at terms. So we've got that this yellow star is equal to n of these terms. And what we started with all the way at the beginning was the n-dimensional Fisher information. And we wanted to prove in the IID case, it was n times the one-dimensional Fisher information. And we did, so happiness ensues. I don't know why I'm talking so fast. This is actually how I usually talk. And for some reason, Zoom makes me kind of zone out, and I realized it, and I was like trying to be who I usually am on Zoom, which is confusing. That's who I usually am. Questions? Let's do an example. How about a gamma distribution? Now I'm going to have to fix one of the parameters because right now we only know how to do the Crimera lower bound for one-dimensional parameters. But even if we knew it in the case of 2 dimensions, that alpha parameter is really hard to get at in the gamma function, although we will later. So as an example, suppose that I have x1 through xn, IID, gamma, like 3 and beta for some parameter beta greater than 0. And I want to find the, for example, let's find the Crimera-Rao lower bound for the variance of all possible unbiased estimators of beta, which is a mouthful, which is why we usually say the Crimera lower bound for beta, but it is not bounding beta. Estimators of beta. Okay, so I'm going to use the fact, I always want to use this in this class because everything is IID. So our n-dimensional Fisher information, which is needed for the denominator, because this is IID, is n times the one-dimensional Fisher information. And the one-dimensional Fisher information can be built up off of the PDF. So let's write down the PDF. So in other words, we don't have to start with the joint PDF anymore. This is 1 over the gamma function of alpha, beta to the alpha, x to the, oh, my beta, I have a beta. I'm sorry, I have an alpha. So this is 1 over gamma of 3, and then, yeah, and then I have beta to the 3, x to the 2, e to the minus beta x on the interval from 0 to infinity. My advice for you last time was to ignore this indicator or keep it in mind in the margin, but you don't take the logs and derivatives of it. All right, yeah, so let me just simplify this so I don't have to drag it around. This is 1 over 2 because gamma of n is n minus 1 factorial. But in fact, I don't have to drag it around. It's going to disappear. Why is it going to disappear? Because the log of this is going to be the log of 1/2. So I'm going to break it all up into all of this product stuff is going to become a sum. And then the log of beta cubed is going to be 3 log beta. And then the log of x squared is going to be 2 log of x. And finally, minus beta x. A lot of this is going to disappear when I take the next derivative, which is why, just like in a maximum likelihood estimation, I could have dropped some constants here with respect to beta. So let's go. The derivative with respect to beta of the log of the single PDF is 0 plus 3 over beta plus 0 minus x. So from that, you can see that if you had wanted to, this is going to disappear. So you could have like left that term out, really. And you could have left this term out because it's going to disappear. Okay, we're ready for the one-dimensional Fisher information. And it goes a little something like this. It is defined, I'm going to do it both ways. I'm going to use the squared and the second derivative methods. So it is defined as the derivative with respect to beta of the log of like f of x1 or any xi or x5, this whole thing squared. This is the expected value of this guy with a capital X or capital XI or capital X1 or an X5. You can just use X and say that represents one of them. But this is 3 over beta minus capital X1 squared, which is, of course, I can reorder this, right? It's squared. So X1 minus 3 over beta squared. And this is almost always in information computations, almost always either a variance or something that can be manipulated into looking like a variance. And note that X1 here is gamma 3 beta. And so this is the expected value for X1, which is alpha over beta. So in this problem, we directly have a variance. You won't always have a variance, but you always, I can't think of when you can't. I'm pretty sure you can always manipulate this by pulling constants around to make it look like a variance that you could just look up in your table. Okay, so the variance for the gamma distribution is alpha over beta squared, which in this case is 3 over beta squared. So the n-dimensional Fisher information, because these guys are IID, this is n times the one-dimensional Fisher information, which is 3n over beta squared. For fun this weekend, you might go through this whole thing with the vector, and you would have a sum of gammas. And we know that the sum of gammas is another gamma, and you'll get through it. But the Crumier-Rao lower bound, the Crumier-Rao lower bound for any kind of tau of beta is tau prime of beta squared over the n-dimensional Fisher information. And in our problem, because we want the Crumier-Rao lower bound for beta, our tau of beta is just beta. So that derivative is just 1 squared over 3n over beta squared. So the Crumier-Rao lower bound for the variance of all unbiased estimators for beta for the gamma distribution with alpha equals 3 is beta squared over 3n. Does that make sense? Once you get over all of this notation, these are really easy in the sense that they are very plug and chug. Like you will never really have to be clever to compute a Crumier-Rao lower bound. So I did want to quickly try the second derivative here. And let me just show you back here. I know it's not easy for me to just scroll back up here for you, but this thing that I took the derivative of with respect to beta came out to be this thing. And if I take a second derivative, it's quite simple. In fact, all of the x's go away. I'm going to try this cut and paste thing again. And I have a million other things with me. So if I were to start here and take the second derivative, that is, of course, the derivative of this derivative. And with respect to beta, I've got 3 beta to the -1. So that second derivative would be -3 beta to the -2. And the x's would completely disappear. And those are the random things in the expectation. So the one-dimensional Fisher information could be taken to be the negative of the expected value of the second derivative. And I have an x1 because I'm combining properties 1 and 2. I'm doing the second derivative property and also the fact that I could get the n-dimensional Fisher information by just looking at the one-dimensional one and multiplying by n. And this is the negative of the expected value of -3 over beta squared. And there is nothing random there. So this is just -3 over beta squared, or with a negative in front, +3 over beta squared. And just like before, I can use IID-ness, IID, to say this is n times one of them. So the Fisher information is 3n over beta squared, which was exactly what we got before, and can be used in the denominator of the Cramér-Rao lower bound. That was definitely easier because we didn't even have to compute an expectation. But sometimes derivatives make things worse in terms of, the x's might not disappear. It might become a more complicated function to take the expectation of. Any questions?
Could you go back up for a second? I was trying to wait. Back to the tau prime beta.
Oh, the tau. Oh.
Yeah, you just had it.
Yeah. Oh, not this. Not this.
Yes. Yeah.
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 So we were finding the Cramér-Rao lower bound for the variance of all unbiased estimators of just beta. So the function of beta was just beta. Is that what you needed?
Yes, thank you.
Other questions? Okay, so I have 2 definitions for you. And then, assuming we have enough time, I'm going to write down a fantabulous list of maximum likelihood estimator properties, which relate to the Cramér-Rao lower bound, which is why we had to take this detour. And we'll prove them next week. So, first definition is one of, we talked last time about if you can have unbiased estimators and you can compute their variance, and it could technically have the smallest possible variance, like it could be an UMVU, and yet that variance could still be larger than the Cramér-Rao lower bound because it is just a lower bound. It's not a tight lower bound. But if the variance of your estimator achieves or attains or equals the Cramér-Rao lower bound, it's pretty special, and we call it an efficient estimator. An unbiased estimator whose variance attains or achieves or is equal, so attains the Cramér-Rao lower bound for the problem, is said to be efficient. Not everyone puts the, so that I'm defining efficiency, not everyone puts unbiasedness into this definition, but the Cramér-Rao lower bound does not make sense for biased estimators. So you can have biased estimators whose variance is actually lower than the Cremier-Rao lower bound. And you might call that a super efficient estimator, which is actually the wrong use of that phrase. um, but yeah, I really think any definition of efficiency should include the word unbiased. That's just my bias. Haha. Okay. So that's just a definition. So I guess I don't have to say makes sense. And then the last definition is about the efficiency of an estimator. The efficiency of an unbiased, estimator. You know, I know it's estimator. I just am always emphasizing estimator versus estimate. So it occurred to me yesterday that you might think that that's how I say estimator. And that's just weird. The efficiency of an unbiased estimator, which is what I'm trying to define, is an unbiased estimator T of tau of theta is the following ratio. It is the Cremier-Rao lower bound for the variance of all unbiased estimators for tau of theta over the variance of your estimator. So assuming you did start with an unbiased estimator, this is always less than or equal to 1, and it's equal to 1 if you have an efficient estimator. Otherwise, it's some fractional value, which gives you how much efficiency you actually have. Like it's only half as efficient as an efficient estimator. Again, you might see someone defining this without requiring unbiasedness. In that case, the variance could actually get below the Cremier-Rao lower bound, and efficiency can take on values greater than 1. So if you ever see that, it's probably because they're not limiting you to unbiased. Okay, I guess there's no questions on that either because it's a definition. So I have one more thing, and that is a great list of properties of MLEs. I tried to say to you that they were better than MMEs, and next week I want to convince you of that. So this is a list of great properties of maximum likelihood estimators. And so it is under certain regularity conditions, and we'll see what these are in the proofs, but they're the same ones that we had to prove the Cremier-Rao lower bound. Regularity conditions that I will list next time. If theta hat, and I want to stress the dependence on n, so theta hat n is an MLE for theta, then we have the following. One is under certain regularity conditions, it exists and is unique. So I don't have to say an MLE, I can say the MLE. So under certain nice conditions, exists and is unique. It's always under regularity conditions, a consistent estimator, which means it converges in probability to theta. Is a consistent estimator of theta. So that's a nice large sample property at least. Now some MMEs are consistent, but you need way more conditions on those, and it's really hard to prove that. The third thing is it is asymptotically unbiased. So you have a problem in your homework right now asking you to show that something is asymptotically unbiased. And just to be clear, what this means is the expected value of the estimator may not be theta, but if you take the limit of that as n goes to infinity, you will get theta. This is too rushed. Oh, yeah.
That's different than consistent.
That is different than consistent. So okay. if you have this going to 0, going to theta, and the variance going to 0, it's definitely consistent. But next time I'll bring examples of not the other way around. So this is not equivalent to consistent. I'm out of time. So the fourth thing was going to be asymptotic efficiency. And to talk about that, we need to, they're always asymptotically efficient. So we need to compute the Cramér-Rao lower bound. But perhaps the most interesting thing is going to be the fifth thing in my list, which was under certain regularity conditions, the MLE is always asymptotically normal with the right mean and the variance equal to the Cramér-Rao lower bound. And so that's going to open up a whole lot of large sample things for us, confidence intervals and hypothesis tests. So many times where we can't find the distribution of the statistic, but if we're working with an MLE, we can say, okay, if things are large, I've got approximately normality, even if you don't have a sample mean in a lot of cases. So if you don't know the distribution of this in order to work your problems, you can say for large samples, I can treat it as a normal. And that will be next time on mathematical statistics. Thank you.
Thanks.
Thanks, Jen.
Mm.